Fibonacci formula and the linear recurrence relations. Two big topics. First, we will derive Fibonacci. First we verify, we not derive. Actually, the first part is the verification part. So verify, verification part. The second, derive. So, two different ways to prove the Fibonacci formula. All right. Verify. We know verification is usually much easier than discovery of the new formula. Verification, we have that formula, right? Yeah. We just verify it. That should be much easier. But discovery, you don't know the formula. So you need to find it. So more challenging. So this part D, we will use the problem. So we try to practice our problem solving skills, methods. So another practice round. All right, so let's start. When we do verification, we want to verify some simple special cases first. At the beginning, let's just verify the simplest a few cases. That's easy. So we always work on the easiest cases. All right. The goal, we want to show the Fibonacci numbers. This formula is correct. Right? Fit the golden ratio. Golden ratio number, so here we need to work on it. All right. It looks not quite easy, because the calculation involving golden ratio, not that easy. All right. Let's do the first step, verification. When n equals to 0, F0, you plug in, so the, phi to the 0, it's 1. 1 minus 1 is 0. So then multiply 1 over root, also 0. So the first step verification, very easy. Second step, when n equals 1, now we need to calculate a little bit. All right. Phi to the first, let's just copy the value, okay? Then plus, because negative, negative, plus. 1 over phi to the first, reciprocal, 2 over 1 plus root 5. Many of you know in this situation, we need to rationalize the denominator. We want to make the denominator a rational number. So this 1 plus root 5, too complicated at the denominator. So usually what people do, so they multiply this. They multiply root 5 minus 1 over root 5 minus 1. Okay? Multiply that fraction. Because it's 1. Okay? So you do not change that fraction. Okay? The same number appears at the numerator and the denominator. So you do not change that fraction. But this number, where you multiply root 5 minus 1, you multiply 1 plus root 5. You get apply the formula, right? 5 minus 1. A plus B times A minus B, right? That formula, okay? So A plus B times A minus B, you apply this formula, equals A squared minus B squared. A here, root 5. B 1, okay? So you can get a squared minus b squared, you get a 4. 4 at the denominator, then cancellation with the numerator 2, so you get a root 5 minus 1 over 2. In that way, then much easier, you add these two numbers because -1, +1 cancel out. Root 5, you have 2 root 5, 2 and this numerator 2 cancel out. Root 5, this root 5 cancel out. So you get a 1. You get a 1. Okay? Yeah. So we verify the second Fibonacci number. All right? Yeah? Two simplest cases. Correct. Yeah. All right? Yeah. Yeah. Then the next one, yeah, the next one, yeah. So let's try another one. Okay. We know we can only verify a small number of cases. Yeah, we cannot verify too many here. Okay. But let's just do 1 or 2 more. All right, here. Yeah. F2, now this time phi squared minus 1 over phi squared. Yeah. Yeah. So phi squared, yeah. 1 over phi squared, yeah, because we did the rationalization before. Yeah. So here we can just use that number. Yeah. Then these two, we can apply the formula to simplify, expand, these two parentheses, right? Yeah. Then cancellation, 5 cancel out, that 1 cancel out, yeah. 2 root 5 plus another 2 root 5, you have 4 root 5, 4 cancel out, root 5, and the, leading part, root 5, cancel out. You also get a 1. Okay? So we'll verify another case. Yeah. The first 3 Fibonacci numbers, yeah, all satisfy the given formula. Yeah. So we have more confidence here. Yeah. All right. Then, yeah. But actually, if we just verify these 3 special cases, yeah, already enough. Yeah. But here, in order to show you some special technique, yeah, so I want to do another verification, but this time I will do it differently. I will do it different from what we are doing here. Yeah. What we are doing here, yeah. Because when the n number becomes larger and larger, it becomes harder and harder, right? Yeah. So here I want to show you just one more, but I won't do it in this way. Okay, I will do it in a different way. So let you see. You can do simplification related to golden ratio in a different way. Okay, yeah. So let me show you next. Verification, step number 4. F3 this time. Yeah, because F3, although you can use the old way to do it, but here I want to show you a new way to do it. All right. Yeah. Phi, the golden ratio, it has special properties. Yeah. Here we want to use the special properties of the golden ratio. Okay. Yeah. Think about what's the special property of golden ratio. How do we find the golden ratio? So we go back to, So here we notice that when the degree is high, it becomes harder. Verification becomes harder, right? Yeah. So based on that observation, we want to bring down the degree. Can we use some special property, golden ratio properties, to bring down the degree number in our golden ratio representations? Yeah. We want to do that. Yeah. All right. how to reduce degree of phi cube? Yeah. We need to recall the equality for the golden ratio. What's the equality? There is a quadratic equation. We use that quadratic equation, we calculate the golden ratio. So let's get to that place. Yeah. All right. These are the two properties of the golden ratio. Yeah. Why? Because phi is a root of this quadratic equation. That means if you plug in phi into this quadratic equation, you get equality, right? Can you convert this equality in two different ways to get these two properties? Yeah. Just move terms around, left to right, right to left, okay? Move terms around. Yeah. Apply some simple algebraic operations. You can get those two properties, yeah? Because sometimes we need to use the first property, sometimes we need to use the second property. Yeah. All right, yeah, let's now apply these two properties. Yeah. Phi cube, now we want to reduce the degree of this phi cube expression. 3, too high. Yeah. So we write it as phi times phi squared. How about that? Phi times phi squared, phi cube. Yeah. But when you see phi squared, can you connect to the second property, phi squared? Replace phi squared by phi plus 1. You reduce the degree, right? Yeah. Let's do it. Phi times parenthesis phi plus 1. Yeah. Yeah. All right? Equals phi squared plus phi. Yeah. All right? The highest degree is 2. See? You bring down from 3 to 2. Okay? But when you see phi squared, you can apply the second property another time, right? To bring down furthermore. All right? Yeah? So you replace phi squared by another phi plus 1, so you get a 2 phi plus 1. This time, the highest term degree only 1. Yeah. So you bring down from degree 3 to degree 1. Yeah. That's a, good improvement. Yeah. Very good improvement. Yeah. All right. That's for the phi cube expression. Yeah. So let's put it aside. Yeah. Let's work on the second expression, 1 over phi cube. Yeah. 1 over phi cube. Yeah. All right. We want to bring down the degree of the denominator. Yeah, degree, denominator. This time in degree at the denominator. Okay? Yeah. Although you can use the similar way, but there is a better way. We know when we have this fraction, phi expression, numerator, denominator, if we want to reduce the degree number at the denominator, we want to do cancellation, right? Cancellation can bring down the degree, okay? Yeah. Now we try to do cancellation. So at the numerator, you see this 1, but our first property, you have that 1, okay? You have that 1 in the first property. So we can replace that 1 by the right-hand side expression, phi squared minus phi, okay? Yeah. After this substitution, you can do cancellation, right? Yeah, because they have common factor phi. Yeah. Now you can do cancellation. So the degree number at the denominator is lower, 1 lower than before, okay? All right. Yeah. Now you want to do another round cancellation. Minus 1, you see 1 again, another 1, right? So you have a second chance to apply the first property. Yeah. All right. Phi minus parenthesis phi squared minus phi, so you get a 2 phi minus phi squared. Okay? Then you do simplification, you get 2 over phi minus 1. Okay? Yeah. This time, much simpler. Okay, much simpler. Yeah. All right. Yeah. Although you may argue, you may want to do another, right? Yeah, it's okay. So because you see, 2 is 2 times 1, right? 1 is phi squared minus phi, so you have another 1 over phi minus 1 equals 2 phi squared, that's 2 phi, yeah, 2 phi minus 3, right? Yeah. Yeah. Moving minus 2. Right? Yeah. You can do that. Yeah. Yeah. All right. Yeah. Yeah. But this is still not easy to see. Yeah. All right. All right. Now, yeah. So that way, yeah. Let's do it directly. Okay. Yeah. After cancellation, right? Yeah. Because this negative 1, that positive 1 cancel out. You factor out the 2, you get this one. All right? Yeah. All right. From this one, this expression, can you see? Yeah. This related to F3, this related to F1, right? Yeah. This part is F1. Because if you multiply 1 over root 5, you get F3. So if you multiply 1 over root 5, you get F1, right? Yeah. So then it tells us F3 equals 2F1, that is 2. So in this way, you can get F3. But this way, not easy to get it. Yeah. That way, yeah, not easy to get. Yeah. Okay, yeah. Sorry, oh, x phi squared, right? Oh, phi, yeah, 2 phi, yeah, not phi squared. Yeah. Yeah, so we use this way, we can get. Yeah. That way, we may not, yeah, so we have some problem. Yeah. Yeah. So using this case, I want to show you, sometimes you can use the properties of the golden ratio to help you bring down the degree. Yeah. All right. Yeah. Because we may have some homework questions, yeah. Quiz or homework or test questions related to the golden ratio. Yeah. So I show you, these examples. Yeah. So you may see, yeah, some related questions in your quiz or homework assignment. Yeah. Okay. Yeah. All right. So we complete verification of the first 4 cases. Yeah. That's enough. Yeah. But next we want to do the verification for the general case. Yeah. All right. The general case, general n. Yeah. You cannot use the concrete numbers. Yeah. The concrete numbers, you can only do relatively small number of verifications. For the general case, you have to use some rigorous way to do the verification. Yeah. So here we are at an important stage. Yeah. So we need to apply some powerful tool for the general case. We rely on some powerful tool to help us to do the verification. Okay, all right. That powerful tool, mathematical induction. Remember, we had this similar situation before, but at that time I delayed it. I said because we will have a second chance, so we merge. So I only show you mathematical induction once. Yeah. So the first time we skip it. Yeah. Now we need to do it. Yeah. Mathematical induction. All right. in the mathematical action, we need to follow the standard method in 3 steps. The first step, we check the base cases. Here we already check it. We check 4 cases. The base cases, we only needed 2 base cases checked because the given initial condition, there are only 2 initial conditions. 2 initial conditions, we only need to check 2 base cases. We don't need to check 4. Yeah. So we did more than necessary for the step 1. All right? F0, F1. Yeah. We did it. Okay? Yeah. Now, yeah. Step 2, we need to make induction assumption. It's an assumption step. Okay? It is an assumption step, induction assumption. Okay? We do not need to do any math work. We just make assumption. Okay? That's step 2. Induction assumption. What's that induction assumption? Yeah. We assume that the formula is true for, yeah. So actually we should assume for those 2 should be 0 less than equal to k less than equal to n. Yeah. If k, when k in this range, yeah, because 0, 1 we already verified, it's true. Okay? Yeah. But in our assumption, we just make redundant assumption, right? Yeah, we know it's true. Yeah, we just the reason we make it 0 because this is the range, in this range, 0 through n. Okay? Yeah. Yeah. And here at the beginning, so let's say at the beginning we can say n greater or equal to 1. How about that? Yeah. The smallest n is 1. Yeah. Because in that range we verify it. Okay? We verify it. Yeah. Then because in future we can grow this n, so this range can grow. Okay? Yeah. That range can grow. Yeah. Yeah. At the beginning, it is 1, but gradually we increase this n number, larger, forever. Yeah. Goes to infinity, this n number can. All right. All right. So our assumption in some range, yeah, k, when k between 0 and n, we have this formula. All right. That is the induction assumption. Yeah. And the starting point of this assumption, the starting point is step 1, base case. Base case is the starting point of our assumption, induction assumption. Okay, all right. Yeah. Then step 3, we need to do the critical. That's the critical step. That's the main work of the mathematical induction. That is step 3. So we need to prove that. Step 3, we need to verify that when k equals n plus 1, k equals n plus 1. Okay. F n plus 1 equals this formula. Yeah. But we need to prove it. We need to verify it. It is correct. Yeah. Okay? Yeah. If we can verify it's correct, then we can show the Fibonacci formula is always true for all the n number n greater or equal to 0. Okay? For n non-negative integers, the Fibonacci formula is true. Okay? Yeah, if we have step 3. Okay? Yeah. All right. But the step 3, we need to prove it. Because we know n plus 1 is out of the range. It's not in the range. Okay? Yeah. Out of the range. Outside that range, not inside the range. Okay? Yeah. That means we expand the range, right? Yeah. If we can show the step 3 is correct. Can we expand the range? So here, what we will do, expand the range. From 0, integer in this interval to a larger n plus 1, right? We expand the range. How about that? Okay? Yeah. Yeah. If you can keep expanding your range in this way, then you can cover all the non-negative integer n. That's the essence of this method. Yeah. We can keep expanding our range in which the Fibonacci formula is true. Yeah. All right, so here you can see we only need to do the last step, then we are done. Okay, all right, so let's do the work. All right. This recurrence relation, it is given. Okay, yeah, we can always use this recurrence relation. Yeah. If it's a Fibonacci number, we can always use this recurrence relation. Okay, yeah. So let's apply this recurrence relation first. All right. Fn plus 1, yeah, because Fn, n is in the range, right? Remember? Yeah. When k in the range between 0 and n, we can apply the formula. Apply the formula, right? Yeah. Yeah. Here, the first one in the range, right? The subscript. Yeah. We can apply the formula. Okay. Yeah. Let's copy the formula. Yeah. And n minus 1 also in the range, right? Yeah. So we can apply formula another time. Okay. Yeah. Now, let's do the simplification. Yeah. Because this formula we want to show is this, whole thing the same as our destination expression. This is our destination. That's our goal. Okay, that's our goal. So we want to verify, this, whole expression the same as that one. Okay, we want to compare. Okay, yeah. All right. When we compare, they should be the same. Yeah. Let's do some simplification. Because they have the factor 1 over root 5. All right? Can we ignore 1 over root 5? Both sides, they have same 1 over root 5 factor, right? Can we take away 1 over root 5? Both sides. Yeah. Because at the end, we can multiply it back. Yeah. Here, we do not need to consider 1 over root 5. So we're simpler. Okay? Yeah. All right. So let's ignore that 1 over root 5. Yeah. All right. Then, inside the big parenthesis, so 1 over root 5 is out. So here also 1 over root 5, 1 over root 5. So we only need to consider everything inside this destination parenthesis the same as the expression inside this big parenthesis. Okay? All right. Yeah. We want to verify. Yeah. All right. Then, when we do the comparison. When we do comparison, yeah, we hope they are the same, but we need to show it. Yeah, show it. Yes. But when we do comparison, we want to compare the integral part with integral part, right? The fractional part with the fractional part, right? Because same structure. Yeah. So that's our understanding. The objects with the similar structure, then we should put them together, right? Yeah, yeah, yeah. The objects with different structure, we should not, yeah, because in general, they should be different. Here, so we separate. The first time, we only compare the terms with the integral form. Both sides comparison. Yeah. So we want to see, is this equality true or not? Okay. Is that the first equality true or not? All right. Yeah. Yeah. Then the second time we want to see if the fractional part, both sides, the same or not. Yeah. 2 steps. Yeah. But the first step, the integral part, that's easy. Yeah, because we have the golden ratio. We have this equality, right? Golden ratio. Phi squared equals phi plus 1. That's our golden ratio. Basic equality. Can we multiply the term phi to the n minus 1 both sides? Multiply that equality by this phi to the n minus 1. Both sides. Left hand side we have phi to the n plus 1. Right hand side phi to the n plus phi to the n minus 1. That's our first equality. Okay? Yeah. So we verify it. Yeah. First one, correct. Yeah. Next, we need to verify the second one. Yeah. If the fractional part from both sides are the same or not. Yeah. A little harder to verify the second one. Yeah. All right. But let's try this way. Yeah, so let's do the comparison work here. Yeah. All right. In order to do the verification, yeah, we want to do verification here. Here we want to apply that backward thinking. Backward thinking. Yeah. Because here we don't know if it's true or not. Yeah. But we can change the form of this expression in an equivalent form. If this is true, then we get an equivalent form. Okay? Yeah. So that's why. So we do that. So equivalent form, we remove the common denominator. Yeah. The first step. Remove the common denominator. Okay? Yeah. All right. So after we remove the common denominator, we have this expression. We multiply phi to the n plus 1 both sides. After simplification, we get this expression. Okay? All right. But that -1, the power of that -1, quite annoying, right? It's distraction. So we want to eliminate that negative power of -1. Okay? Yeah. To simplify it. Yeah. To do that, we multiply both sides by -1 to the n minus 1. That power function, appropriate power function. Yeah. Then when we multiply left-hand side, because the exponent becomes even number, -1 to some even number, it is +1. Okay? Yeah. So then, yeah. Then, odd, we look at the exponent number, odd, even. For odd, it's a negative term. For even, a positive term. So we need to verify 1 equals phi squared minus phi, and we know this is one of the properties, right? Yeah. We know this is one of the 2 properties of the golden ratio. So it is true. Okay? It is true. Then, all these transformations are equivalent transformations. We can go both sides, okay? Because the last one is true, we can go backward. The previous one also true because they're equivalent, okay? Then another, we go backward, yeah. Another, its previous equivalent is true, yeah. So that's what we need. Yeah. This one is what we need, okay? Yeah. So we verify both parts. Integral part the fractional part, both parts correct, then that means our final conclusion, this equals that. This whole thing is correct. Okay? Yeah, so we're done. Yeah. So we complete the verification by that mathematical induction. Yeah. Yeah. All right? Yeah. So that's the power of mathematical induction. Otherwise, how can you prove it? Right? Yeah. How can you rigorously prove it? Yeah. Yeah. So this mathematical induction is very important. Okay? All right? I just show you once in this class. Okay? Yeah. Yeah. Let you know so you have this powerful tool when you need it. Okay? Yeah. All right. Yeah. So let's move to our next topic, D.3, linear recurrence relation. This time, we want to discover the formula. Yeah? Because verification, you need someone who tells you the correct formula, right? Yeah? But someone must discover it first, right? Yeah. Yeah. The first person needs to discover the formula. Yeah. Here, so let's look at the discovery. Portion of this formula. Yeah. All right. Here, we need to solve the linear recurrence relation. How to solve linear recurrence relation. Yeah. Yeah. So using this example, so we review. Because in discrete math, there is a section you study this topic. Yeah. But here we do it another time. Yeah. So here we from the problem solving point of view. Yeah. Yeah. In discrete math, so you may not understand from the problem solving. You just follow the standard procedure, step 1, 2, 3, 4, find a solution. But why are you doing that way? Yeah, most of you may not know. Yeah. We just follow the steps. Yeah. Yeah. All right. Here, I want to explain from the problem solving that special view we want to understand. Yeah. All right. Yeah. But at the beginning, I want to do a simpler version, solve the recurrence relation for the Tower of Hanoi. We didn't do it, right? Yeah. So we derived. So we derived. This is a recurrence relation. Yeah. But we never did it. Yeah. So here I like to, I like to show you how to do it. Yeah. All right. Yeah. 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 All right. Some students, they know to solving this one, people can use the characteristic equation to do it. Yeah, yeah, good. That's the standard way. Yeah. But here I want to do the problem solving. Yeah, so try to solve the problem based on our usual problem solving approach. Yeah. All right. We want to solve this equation. Okay. All right. Now, the first step in problem solving, you need to spend some time to do the observation to understand the structure of the equation. Yeah. Understand the structure of the equation. Okay? All right. So here. Now, some important observation. Yeah. In this equation, there is a special term, this +1 term. That term is very special. Yeah. Yeah. So we want to see the role of this +1, the role. Okay? Yeah. Think about, without that plus rho, is it easier to solve? Yeah. Think about, if if we drop that plus 1 term, okay, C of n equals 2 times C of n minus 1. Do you feel easier to solve? Yeah. Without plus 1. Okay? Yeah? Because you just do iteration. Keep doing iteration, right? Every time you multiply by 2. Every time you multiply by 2. So it's easier to solve. Okay? Yeah. All right. So here, see, I want to show you a little bit. Okay? All right. C of n equals 2 times C of n minus 1. Yeah. Yeah. All right. The second time, 2 squared times C of n minus 2, right? Next time, 2 cubed times C of n minus 3, and so on. Okay? All right. Now, we can keep doing every time multiply by 2, but we reduce the number inside the parentheses by 1. Yeah. We increase the exponent number of 2 by 1, reduce by 1. Then, the last one, because we want the C inside parenthesis, we want to make it a 1. That's the base number. So what is the exponent of this power of 2? What is exponent if it's 1 here? Is it n minus 1 or n? N or n minus 1? Yeah. All right. So here, exponent. Remember, we learned a technique, problem-solving technique called the invariance concept. Invariance. We try to find the invariance property. Okay? All right. So here, the invariance, the superscript 1 plus the number inside parentheses n minus 1 equals n, right? If you do the same thing, superscript 2 plus the number inside parentheses n minus 2, you also get n, right? That's the invariance, okay? These two numbers adding together, invariance. Yeah. But now, this number is 1 here, so one number should be here. Superscript. The sum is n. Yes. N minus 1, not n. Yeah. So here you can see, here we apply that invariance property. We can keep track of our data. Otherwise, you get lost, right? You couldn't keep track of it. But if you can find that invariance property, you can keep track of it. Okay? Yeah. Yeah. All right? Yeah. Review. Yeah. So that method. All right. So this tells us, yeah, if that plus 1 is gone, we can find solution, yeah, easily, right? Yeah. So that means that plus 1 adds some difficulty to this problem. Yeah. That plus 1 makes this recurrence equation harder to solve. Okay? All right. Yeah. All right. The next thing is, here we are given with this plus 1 term, can we use some technique to make it disappear? Well, we want to make that plus 1 term disappear. Is that possible? Disappear. Then we know how to solve it. Okay? So here, one thing is, we need to apply some special mathematical operation to make that plus 1 disappear. All right, yeah. Think about that. Okay, all right. The method is, we plus 1 both sides. How about that? in that equation, the two sides, we can add 1 both sides and see what happened. Okay, here, let me show you. Oh, sorry. Yeah. Plus 1 both sides. Yeah. Left-hand side, C of m plus 1 equals the right-hand side 2 times C of m minus 1 plus 2, right? Plus 2. Okay. 2, you see, 2 here and there. Can you factorize common factor 2 out? C of m minus 1 plus 1. Can you get that? After that, can you see some nice progress we have? Yeah, after this transformation, we get something interesting. Yeah. Because look at the left-hand side, C of m plus 1. Look at the right, 2 times C of m minus 1 plus 1. Yeah. Same structure, right? Is the same structure? Same structure. If the same structure, can we introduce a new function to represent this structure? We let it d of n equals C of m plus 1. Can we introduce one? Then this one, can we represent it as a d of n minus 1? Right? If you can do that, now your equation becomes d of n equals 2 times d of n minus 1, right? That plus 1 term gone, right? Yeah? We make it disappear. See? After we introduce a new function, we make that plus 1 term gone. All right? Yeah. And solving this is easy. We have the confidence, right? Yeah. But solving this one, because this time d of 1, you need to update its initial value. D of 1 equals C of 1 plus 1. So it is 2. It's not 1. Okay? So you need to change. It's 2. Yeah. But based on our old invariance way, 2 to the m minus 1 times d of 1, right? 2 to the m minus 1, d of 1. Yeah. Using our, old way. But d of 1 is 2, right? Yeah. d of 1 is 2. So you get a 2 to the n. Yeah. So d of n function is 2 to the n. But you need to go back to the C of n function equals d of n minus 1, so equals 2 to the n minus 1. Okay? That's the final solution. Final solution. C of n, yeah, the number of moves when you solve that Tower of Hanoi problem with n disks, you need 2 to the n minus 1 number of moves. Final conclusion. Final conclusion. Okay? That's how we derive it. See? Yeah. That constant term, here you can see that constant term. If it's not 0, we need to make it 0 first. Okay? Yeah. So here we have a term. If it's not 0, if it's 0, we call it homogeneous equation. Okay? So there is a term called homogeneous equation. Yeah. Homogeneous means the constant term is 0. No constant term. Yeah. If you have a constant term, so we call it non-homogeneous recurrence relation. Yeah. So here you can see, we want to solve a homogeneous recurrence relation first. If we have a non-homogeneous, we need to convert it. We need to convert it or consider the homogeneous version. We solve that first. Then we want to see what's the connection between the homogeneous version and the non-homogeneous version. Then the difference, here the difference is difference by 1. The homogeneous solution and non-homogeneous, the difference is by 1. Yeah. So we find that solution. Okay, all right. But that's the Tower of Hanoi problem. Okay, yeah. All right. Now let's move to our Fibonacci number problem. It's much harder than the Tower of Hanoi problem. Yeah. All right. Yeah. This time, the good thing is we have the experience, right? Yeah. The solution. Yeah. We have experience solving the Tower of Hanoi. We use that experience to help us to solve this Fibonacci number, the problem. Yeah. All right. This time, yeah, the name of this equation. Yeah. So here you can see the long name of this equation. Okay. This equation. Okay. Second order, linear, homogeneous, linear, linear, homogeneous, because the constant term is 0, no constant term. So it's homogeneous. Recurrence relation with constant coefficient. Yeah. That's the name of this equation. Okay? Yeah. Yeah. Homogeneous. So the given equation is homogeneous. So we do not need to do conversion. Okay? We do not need to do anything to make the constant term disappear. Right? Yeah. Yeah. All right? Yeah. Yeah. Now, let us solve this equation directly. Yeah. A general representation of equation like this, we can use capital A, capital B represent. The second order, yeah, because here, the right-hand side, you have two consecutive terms at the right-hand side. Okay? Yeah. All right. Yeah. And for our Fibonacci numbers, capital A, capital B equals 1. Yeah. So you can see it's a simple recurrence relation. A very simple second order recurrence relation. Okay? Yeah? All right. Now, we need to solve the Fibonacci recurrence relation. All right. Yeah. So that's our goal. We want to solve this one. Okay. All right. To solve that one, from the problem-solving point of view, what should we do? So when we have this difficult problem, what should we do? Based on the problem-solving thinking. Yeah. So we get, practice training in this class again and again. Problem-solving thinking. Okay? All right. Yeah. Let's take a special view. Yeah. So here, yeah. To solve this problem, we need to use our imagination, our experience. Experience is useful. Imagination is important. Yeah. When you have experience, then you need to apply your experience at the right time. Okay? Yeah. So not in a random way. Yeah. You have to apply your precious experience at a key point. Okay? Yeah. All right. So here, let's consider, because the Fibonacci numbers, can we put them together so we get a sequence of Fibonacci numbers? So here we'll consider a sequence. Fibonacci number as a sequence. Yeah. Here, this sequence is our data. Okay? So that is our data. Here we want to understand our data. Okay? Data, our data. We want to understand it. Yeah, all right. Yeah. Think about what the specific form in your data. The Fibonacci number, does it take some special form? Think about that. The special form of the data. It's hard, right? You have no idea. What's the special form of your data? You don't have any idea. Okay? Yeah. So this part is hard because this part you need to apply your imagination. Yeah, that's very hard. Okay. All right. Now let's make a connection. Let's make a connection. All right. All right. This is the second order recurrence, homogeneous second order recurrence relation, linear. Okay. All right. But we have the experience of homogeneous first order recurrence relation, right? We have the experience. Okay. All right. Yeah. So here, think about. Yeah. A sub k equals 2 times A sub k minus 1. That's the homogeneous first order recurrence equation we considered before, right? Yeah. Considered before. And we know the solution is 2 to the n minus 1, or n. Yeah. So you can see the solution is the power of 2. Solution of our first homogeneous recurrence relation is the power of 2. Okay? That's the form of the, because if you write your solution as a sequence, you get a power of 2, right? Sequence, right? Yeah. Your sequence takes the form power of 2 sequence. Okay? Yeah. Can you use that experience to help you to get some idea for our current problem? Yeah. How do we model the data here? Here we want to model the data. Model data, we want to choose some appropriate form for our data. Based on our experience from first order linear recurrence relation. It's a power function, right? It's a power function. Can we make a reasonable assumption or extension, make a reasonable extension? The form of our second order recurrence relation, the solution number, also power function. Can we use power function to model the solution? Power function to model the solution. How about that? Yeah. Okay. Yeah. Because in problem solving, when we make connection, sometimes we need to make some very, brave steps. Okay? Yeah. Yeah. So if you worry about too much, you don't want to try this, try that, you can go nowhere, right? Here, when you try to, you need to make some very brave move. Yeah, here. Okay? Yeah. All right. So here, our important step, we want to use power function to model the solution data. Okay, power function. All right. Power function may not be the power of 2. Power of 2 is just special example. Power of some number. Power of some number. Some unknown number. We don't know. What's that number? We don't know. But just the power form. Okay? Yeah. Power function form. All right. Yeah. So we guess the structure. That's because our guess, we're based on our own experience. It's not a baseless guess, right? Yeah. So we have our own experience. That's the base of our guess. All right. The power function. Yeah. T to the kth power. Yeah. Yeah. That's the model. Okay. We use power function to model our data. Yeah. All right. Yeah. All right. But T is unknown. We don't know what is the T number. T is unknown. Okay? Yeah, so here we know this is a geometric sequence. That's the model of our data. Okay? All right. Now, we want to see if this model works or not. It may not work, right? You may create a wrong model. Your model could be wrong. If the model is wrong, you get nothing. Okay? Yeah. So here, we want to try if this model works or not. All right? Yeah. All right. Let's plug in. Okay? Yeah. If a sub k equals t to the k, this power function, let's plug in. How about that? Okay? Yeah. Plug in. Yeah. Can we solve this equation if we plug in? Right? Yeah. If we plug in, we get this equation. We just solve it. Okay? And we know it's a solution, right? After simplification, the equation becomes t squared equals t plus 1. We are familiar with this equation. Yeah. We know this solution has two possible solutions, right? Yeah. Quadratic. Yeah. Yeah. So we solve this quadratic equation. There are two solutions. First, T1, 1 plus root 5 over 2. Golden ratio. But another one, T2, 1 minus root 5 over 2. There are two possible solutions. Okay? Yeah. So for two possible solutions, the question, which one should we use? Which solution should we use? The plus version, positive version, non-negative version? Non-negative version, here we should be careful. Because if you say positive version, no negative, you throw away negative version, right? Can you explain, can you justify it, why you can throw away the negative version? Because here, when we talk about the golden ratio, the reason we can throw away, because we know that golden ratio, that's the ratio of two line segments, right? That cannot be negative, right? But here, this T1, T2, we do not connect to ratio of two line segments, right? Nothing to do with the line segment, right? Why it cannot be the negative? Nothing to do with ratio of line segments. No such restriction. No reason to throw away. Okay? There is no reason to throw away. So you should keep it. You should keep it. Okay? That means we have two solutions. T1 is the solution, T2 also solution. Two valid solutions. Two solutions for this recurrence relation. Both satisfy recurrence relation. Okay? Yeah? So we should keep both. Keep both. Okay? Yeah. All right. Then let's move to next step. Yeah. So here you see in this first step, modeling, our data modeling. Here you can see that's what we did at this point. We call it data modeling. So you know the importance of the data modeling. Okay? Yeah. Because we just describe our data using a special structure. Here the structure is the power function structure. That's our modeling step. All right. After we complete the modeling step, now we need to move to this next step. All right. Yeah. So this step here, yeah, we have two special solutions. Yeah. Yeah. All right. The T1, T2. Yeah. Specifically, the first solution, if we plug in the first solution, this recurrence relation is satisfied, right? Then we plug in the second solution, T2, this recursive relation is also satisfied. All right. Yeah. The next question is, we have nice progress here. Okay? Yeah. We have two special solutions. Yeah. The next question is, can we use these two solutions, two known solutions, to represent more other solutions? Because we want to find all the possible solutions. Can we use the two known solutions to get more other solutions? That's the question. Think about that. Because two solutions we feel not enough. We want to find all the possible solutions. Can we do that? All the possible solutions. Based on the two, because the two known solutions, we should use these two solutions to help us find new solutions. That's our goal. You can use two old solutions to find new solutions. How to do that? How to do that? This equation has an important property. We want to take advantage of it. This recurrence relation, we call the linear recurrence relation, right? Linear, homogeneous linear recurrence relation. That's the equation type. Now we want to take advantage of the linear homogeneous equation, this property. How to use it? The linear property. Okay? Yeah. So it has the property we call the linear radius property. Linear radius property. This linear radius property. Now we want to take advantage of this linear radius property. Okay? Yeah. Yeah. So let me just use a few words to give you the idea. The linear radius, how do we take advantage of this linear radius property? Yeah. All right. Yeah. All right. Yeah. So here, although some of you may check initial condition because these two solutions, they do not satisfy initial condition. They're not integers, right? Yeah. They're not integers. Okay? Yeah. But don't worry, that's the reason we want to find new solutions. If we can find all the new solutions, do we have a chance to find integer solutions in the new solutions? Yeah. Because these two old solutions, they are not integers. Can we use two old solutions to form new solutions, and hopefully in the new solutions we can find some integer solutions? That's the point. That's why we want to find new solutions. Why you find? Because only in the new solutions we have a chance to get integer solutions, right? Yeah. So, all right. Yeah. All right. So let me stop right here. Yeah, because the story is pretty long. So next time I try to complete the remaining part of the story. Yeah. But next time, remember our midterm is 1 week from today, right? Yeah. But next time I want to spend most of our time. Yeah. Let's forget about this. Let's recover the story after midterm. Okay? Because next time I want to do the review, talking about your homework questions. So we do not waste time on this part. Because you won't have the questions in the midterm, these questions in the midterm. Yeah. So we can delay after midterm. All right? Yeah. So just focus on the midterm.